guys, Miss Miklos here, and today we are starting our first lecture in Chapter 9, and we're going to be talking about graphing simple rational functions. And just a few things, we may remember that the word rational means anything we can write as a fraction of integers. So we're going to be dealing with fractional functions. So I know those are two of our favorite things, so it's going to be a great day. And today we're really just focusing on some basic rational functions, and we're going to talk about how we find the asymptotes for the functions and how we figure out the domain and also the range for these particular functions. So if you haven't already, please go ahead and download this note handout, which is available on MyOlu. And we're going to start by talking about the form of a rational function. So a rational function is of the form f of x equals p of x divided by q of x. So basically what this is telling me is that we have a fraction here which consists of two different functions. And it's very important to realize that the denominator cannot be equal to 0. Okay, so that's kind of a key thing for us in figuring out our domain today, because we know that we can never have division of 0. And this graph is going to make a new shape. It's going to kind of look like two parabolas that are interesting, kind of sideways, and we call it a hyperbola. And we will learn a lot more about hyperbolas later in this semester. So here's the first of the two different equations we're going to be dealing with today. Notice we have a fraction plus a constant. Okay, so we talked last chapter about asymptotes, how those are lines that our function is going to approach but never actually reach. And we're going to have both vertical and horizontal asymptotes. So if we look at this, our vertical asymptote is going to be at x equals h. So what that means is I'm going to have to set my denominator equal to 0 and get x by itself. Our horizontal asymptote is going to be at y equals k, and k is going to be whatever that constant value is. Okay, so knowing these asymptotes is going to become very important in how we go about graphing the function. So number one, it says graph and state the domain and range. In order to graph it, the very first thing we are always going to do is figure out what the asymptotes are. We said our vertical asymptote is x equals h. So what I'm going to do to find that, I'm going to take this denominator, x plus 3, and I'm going to set it equal to 0. So that means that x equals negative 3 is our vertical asymptote. It is extremely important that I write this as an equation. It's not just a number because I am showing that it is all the x values of negative 3. So it is a line, it's not just a point or an ordered pair. Now to find my horizontal asymptote, I'm going to set y equal to the constant. So I'm going to go ahead, there we go, and I'm going to write y equals negative 1. Okay, so these are going to become some important values when we're figuring out how to actually graph this function. So the very first thing I'm going to do is graph these two lines on our graph. So here I graphed our horizontal asymptote of y equals negative 1, and here's our vertical asymptote of x equals negative 3. So the next thing we're going to have to do, we honestly have no clue how to graph this, so we are going to rely on an XY chart, which is always our go-to if we don't know how to graph something. And the way that we're going to go about doing this, I want to go ahead and we're going to make it really simple. We're going to just have to plot 4 different ordered pairs. Okay, so we're making this kind of as basic as it can get. I'm going to choose 2 points that are to the left of our asymptote and 2 points to the right of the asymptote. So in this case, I would probably use values like negative 2, negative 1, negative 4, and negative 5. So I just inputted those into our X chart here, and I need to figure out what the y value is. So I'm substituting these values in for x. So our first one is going to be y equals -2 over the quantity -1 plus 3 minus 1. So when I combine those, I get 2. So I get -1 minus 1, which is -2. So my first ordered pair is going to be -1, -2. So now I'm going to go ahead and substitute in -2. So I get y equals -2 over 1 minus 1. So y is equal to -3. So this tells me y is -3. So I have an ordered pair of -2, -3. So we have successfully found the two ordered pairs that we're going to use that are to the right of our asymptote. Now I'm moving to x equals -4. So when I substitute that in, I get -2 over -1 minus 1. So I get 2 minus 1, which is 1. So that gives me an ordered pair of -4, 1. So now we're finding these ordered pairs that are on the left of our asymptote. And last but not least here, I'm substituting in -5. So I get -2 over -2 minus 1, which is 1 minus 1 or 0. So I get -5, 0 as another ordered pair. So now we're going to go ahead and we're going to plot these on our graph. Okay, so we had -1, -2. We also had -2, -3. -4, +1. And -5, 0. So this is kind of an interesting shape, and what we will see is that if we pretended that our asymptotes were like the x and y axis, for example, would be like quadrant 1, quadrant 2, quadrant 3, and quadrant 4, we will notice that our graph is always either going to be in 1 and 3 or in 2 and 4. So they are going to be diagonal from one another. And what we're going to do here is go ahead and graph what is going to look like two parabolas that are getting close to the asymptote but not actually touching them. Okay, and so what this is telling us, as we get close to this value of -3, it's going to get very close to infinity. Okay, it's never actually going to touch this. And as we go to the left, it is going to get very close to -1 but never actually reach that. Same thing over here. As we go to the left, it's going to go down to -infinity, and as we go to the right, it's going to get close to -1 but never cross the asymptote. Okay, and this is what it will always look like. If we had wanted to plot more points, we could have, and we could have gotten a more accurate picture. Now, I just want to bring this into context of extraneous solutions, which will come up this chapter once again. But we've talked a little bit about the graph dealing with extraneous solutions, and it deals with our domain. If we look, we know that our x value cannot equal -3. That means that if we graph this, the function does not exist at that value. Therefore, if I had solved an equation and got -3 as my answer, we would say that is extraneous because I can clearly see this function does not exist there. So we're actually going to go ahead and talk about our domain. So I'm going to say our domain, which remember is our x values. And we're really used to saying our domain is -infinity to +infinity. But we can clearly see there's one x value that doesn't work, and that is -3. So I'm going to say it's going from -infinity to -3 union -3 to +infinity. Remember, we use this union symbol when we have two different parts of our graph. Secondly, remember we use parentheses when that value is not included. It's just kind of like a boundary. Our range, okay, we notice that it's going all the way down to -infinity and it's going up to +infinity. The only y value that it does not hit is a y value of -1. So we're going to go ahead and say this goes from negative infinity to negative 1, union negative 1 to infinity. Okay, so we notice that our two different asymptotes become really important when we're writing our domain and our range. The second type of equation we're going to see is a little bit more complex. This time, notice I don't just have a number over x plus whatever plus a constant. We have y equals ax plus b over cx plus d. This time, once again, our vertical asymptote is when the denominator is equal to 0. Our horizontal asymptote is the ratio of our x coefficients. So that would be y equals a over c. So let's look at number 2. Number 2, to find the vertical asymptote, I am taking our denominator and setting it equal to 0. So I get 2x equals 4, so x equals 2. So my vertical asymptote is x equals 2. Our horizontal asymptote is going to be the ratio of these coefficients. So I'm going to go ahead and say 1 over 2, which we cannot simplify at all, so it's going to be at y equals 1/2. So let's go ahead and plot these on our graph. So x equals 2 gives me a vertical line at x equals 2. And y equals 1/2 gives me a horizontal line at a value of 1/2. So now I want to choose 2 points to the right of this asymptote and 2 points to the left. So I'm probably going to use 0, 1, 3, and 4 just because I like being as close as possible because the values are going to be nice. So we're going to try 0, 1, 3, and 4. So if I substitute those in, y equals 0 plus 1 over 2 times 0 minus 4, I get negative 1/4. So 0, negative 1/4 is a solution here. Now let's try 1. So I'm going to get y equals 1 plus 1 over 2 times 1 minus 4. So y equals 2 over negative 2, which would be negative 1. So we also have an ordered pair here of 1, negative 1. Now I'm substituting in 3, so I get 4 over 6 minus 4, which is, I don't know why I just wrote 3. It would be 4 over 2, which is 2. So 3, 2 is also going to be an ordered pair. Lastly, I'm substituting in 4. So I'm getting 4 plus 1 over 2 times 4 minus 4. So I get 5 over 4, which is going to be my y value. So now we're going to go ahead and plot these ordered pairs. So I have 0, negative 1/4, and I have 1, negative 1. So I can kind of see that this portion is looking something like this. The second part I have 3, 2, and I have 4 and 1/4. So I'm going to go ahead and plot that as well. So now if we look at this, I can go ahead and write that our domain appears to be every number except for 2. So we're going to write negative infinity to 2, union 2 to infinity. Our range appears to be every value except for 1/2. So I'm going to do negative infinity to 1/2, 1/2 to infinity. Okay, so once again, the key thing here is making sure I know how to find these asymptotes. Then I'm choosing 2x values to the left, 2x values to the right, figuring out our domain and range. So number 3, we can tell that we have a binomial in the numerator and denominator. So this is going to be like the second example we did. So first thing I'm going to do is find the asymptotes. So I'm setting my denominator equal to 0. So my vertical asymptote is going to be at x equals 3. And remember, the reason why I'm doing this is because I know we can never divide by 0. To find our horizontal asymptote, I'm taking the coefficients of the x's and I'm dealing with that ratio. So in this case, I get 1 over 1, which is 1. So let's go ahead and plot these. Okay, x equals 3. We have a vertical line here at 3. And I know sometimes when I'm making this video, the line is slightly off, but hopefully we're understanding where that's at. Okay, and then I have a horizontal asymptote at y equals 1. So some ordered pairs that I'm going to want to use, 2 pairs to the right, 2 pairs to the left. So let's try 1, 2, 4, and 5. So if I'm putting this in, I'm going to say y equals 1 plus 2 over 1 minus 3. So I get 3 over negative 2. Next, we're going to substitute in 2. So I get y equals 2 plus 2 over 2 minus 3. So I get 4 over negative 1, which is negative 4. Okay, so y equals 4 plus 2 over 4 minus 3. So I get 6 over 1, so y is equal to 6. And lastly, we have y equals 5 plus 2, which is 7 over 5 minus 3, which is 4. So I get 7/4. So let's go ahead and plot these. So I have 1, negative 3 halves, and I have 2, negative 4. So we can kind of see that it's looking something like this, where I'm getting close to those asymptotes but not actually touching them. Okay, at 4 we have a value of 6, and at 5 I have 1 and 3/4. So once again we can kind of see that we are making this U-type shape that's getting close to the asymptotes but not actually touching them. Our domain, it appears that the only x value that does not exist is 3. So I'm going to say negative infinity to 3, union 3 to infinity. For our range, it appears that the only y value that does not exist is 1. So we're going to say negative infinity to 1, union 1 to infinity. So we're going to do one final problem, and we're going to see it's exactly like what we just did. A lot of this is just repetition, making sure we understand how to do it. So number 4, I'm going to go ahead and set my denominator equal to 0. So I get 4x equals 12. So x equals 3 is our vertical asymptote. For our horizontal asymptote, I'm taking the coefficients, and I get y equals negative 3/4. So I'm going to go ahead and plot those right away on my graph. Okay, and x equals 3. There we go. So I'm going to try values like 1 and 2 and 4 and 5. And hopefully if I put those in correctly, we will find the ordered pairs. So I have y equals negative 3 times 1 plus 10 over 4 times 1 minus 12. So I get negative 3 plus 10 over 4 minus 12. So I get 7 over negative 8. So negative 7/8 is going to be our y value. Next, we're going to find the y value when x equals 2. And as you can see, I just kind of went ahead and wrote all the work out here. So I substituted in. I got negative 6 plus 10 over 8 minus 12. 4 over negative 4 is negative 1. So negative 1 is our y value. Now we need to find the ordered pair when x is equal to 4. So I went ahead and substituted in. And then I get negative 12 plus 10 over 16 minus 12. So y equals negative 2 over 4, or negative 1/2. And last but not least, I'm substituting 5 in here. So I have negative 15 plus 10 over 20 minus 12. So negative 5 over 8 is that y value. So let's plot these ordered pairs. Okay, I have 1 7/8. I'm sorry. That should be 1 negative 7/8. Let's fix that. Which we notice is getting really close to that asymptote, but it's not actually touching it. And then 2 negative 1. So we can see that this one is very close to the asymptotes. The other one is going to be 4 negative 1/2, which is going to be just above that asymptote. And then 5 negative 5/8, which is even closer to the asymptote. So that is what our function here would look like. Our domain is going to be negative infinity to 3, union 3 to infinity. And our range is going to be negative infinity to negative 1/2, union negative 1/2 to infinity. So hopefully you guys are seeing the repetition in our graph. And the whole point of us knowing how to graph, it's really important we visualize why different answers end up being extraneous.